Yes, yes, ma'am.
Okay. So now I can start. So in the first lecture,
Couple of,
uh,
ma'am, I have a question, ma'am. I have a question, ma'am. Ma'am, will
yeah,
what you teach today in today's class also be included in the Wednesday syllabus?
up to the last class, Saturday, what I have done up to that. So for
Okay,
that
ma'am.
reason, I am trying to recap some lecture one and lecture two. After that, and lecture
Okay,
three will not be included in your syllabus.
okay, ma'am. Okay, thank you.
Okay. Now, in the lecture one, I have explained that different type of the memory chip and what are the pins are possible. And you remember all the memory chip has some address lines and data lines and some control lines. ROM doesn't have the write enable line. It has only the read enable line. But for RAM, this is the random access memory. That's why it has both the pin, that is write enable and the read enable. Okay. Another pin is very important, that is chip select line to select the chip. So normally that chip select line is active low enable, that is CS bar, that will be 0 on that moment, that chip will be enabled. Now, these are the different type of the ICs available in the market. No need to remember all the IC name. Okay, only you try to understand the what are the different possibilities for having the different type of address pins and data pins. For that reason, I have given this table. No need to remember any IC number, okay, and also the number of pins and what are the pins are available for what purpose, okay. Now from the address lines and data pins, you can compute the size 2 to the power n into m. Now it is one type of the IC. Normally we have the 8 bits, but here we have the 4 bits data bus. So 2 to the power 10 into 4, we have the 1K by 4 or equals to 4 KB memory chip. Now sometimes it may be happen only one write enable line you have in your RAM chip, and that will serve both the purpose for write and also the read. Write enable line 0, on that moment it will be RAM can do the write operation, and it is 0, on that moment it will do the read operation. Now different different logic devices sometimes we need whenever we design different type of the memory subsystems. Now here decoder circuit, if number of input is 2, obviously number of outputs will be 2 to the power 2 equals to 4. And here we have considered all the active low enable line. Now it is a 3 to 8 decoder circuit. So obviously 2 to the power 3 equals to 8 output lines. All output lines are the active low, because we consider this type of the decoder circuit uh, for designing the memory subsystem, where you have one of the pin, that is chip select line, and that will be enabled with the help of logic value 0. So that's why active low output line we are trying to consider for the decoder circuit. And another thing is that there may be more than one enable line. Okay, instead of one enable line, you may have more than one enable line. So if you have the two enable line, so 2 to the power 2, that means four combinations of your enable line you can have. You may have active low enable line. You may have active low, active high enable line. You may have active high and active high line. So from the configuration or from the name, you can understand that what type of the enable line. If I suppose write the E, that means it is an active high enable line. If I write E bar, that means active 0 enable line. In that way, you can understand from the figure. So this is a function of 3 to 8 decoder. And it is what I have told, that from the address line data line you can find out the size. Here is from the size you can determine the address lines and data lines. Formula is the same, 2 to the power n into m. Now this is 1k by 4. Okay, that this part, yeah, how many memory chips will be required to design a memory subsystem? Here 1k by 8, suppose we want to design. Now you have the 1k by 4. How you can compute the number of chips required? That is the required memory divided by the given memory. Okay, in that way you can compute the number of chips required. So this you can do. Now, I have told that number of chips, sometimes it may be k. K will be the fractional value. Don't worry about that. You just consider the nearest integer. Okay. So sometimes it may be happen you don't have the k is an integer value. If you don't have, you just consider the nearest integer. Now, it is a simple figure. Only you remember 2 to the power n and m, where A0, if you consider the A0 is the first address bit, so last address will be a n minus 1, and same as for your data bits, that is first bit is d0, so n bit will be dm minus 1. Now, this is one example, that is 64 KB we want to design with the help of 32 KB EEPROM and 32 KB RAM. Now, so our requirement is that 64 KB. So from that information, easily you can compute the number of address bits and number of data bits. So ultimately, we want to design a memory system where you have the address lines 16, A0 to F15. This is ultimate requirement our. Okay, so now now we try to find out what are the address bus available in our memory. So 32 KB EEPROM and 32 KB RAM chip, if you compute 2 to the power n by m with the help of this formula, then you can find out n equals to 15. That means number of address line will be 15. So on that moment, A0 to A14, you don't have a 15 line for your EEPROM and RAM chip. Address lines are the same, but sorry, the data lines are the same, but address lines are the different. So for that reason, what we can do, A0 to A14, directly we can connect to the memory. A15, we cannot connect to the memory because A15 line doesn't exist in your memory. This A15 line we can use for your chip selection. When A15 equals to 0, on that moment you want to select the first chip, that is chip 0. And A15 equals to 1, on that moment you want to select the second chip, that is chip number 1. Now, with the help of this setup, what will be the address ranges for your chip 0 and chip 1? So for chip 0, starting address is 0, that means 0000H, then end address will be 7FFH. Why it is happened? A15 cannot change. During this range, always A15 will be 0. Suppose it is 1, then that address will not be considered as a address of your chip 0. Maybe that may be another that may be the address of the another chip. Okay, so for that reason, A15 will be 0, remaining 0 for all the addresses of the address range 00000 to 7FFFH. So all zeros to all one, it is possible when you have the all address lines in your memory on that moment. Okay, now for the second chip, that is a chip number 1, A15 will be 1. So when A15 will be 1, on that moment A0 to A14, starting address will be all zeros and ending address will be all 1. End address will be all 1. So in that way, if you compute on that moment, starting address, you can say that 8000H, H represent the hexadecimal number, and end address will be your FFFFH. Okay, so all will be 1. So chip 0 to 7 FFH, and for chip 1 8000H to FFFH. So depends on the number of address bits, you can use the 4-digit hexadecimal number, or you may use the 3-digit hexadecimal number, or you may use the 2-digit hexadecimal number based on your number of address lines available. Okay. Now this is the design of your circuit. Here you can see that EEPROM and RAM has the address lines A0 to A14. That means all total 15 address lines it has. And last address, what we need for designing our required subsystem, that is A15. If A15 is 0, on that moment, if EEPROM will be selected, RAM will not be selected, and A15 is 1, on that moment, CS bar of your RAM chip will be 0, so RAM will be selected. EEPROM, CS bar of EEPROM will be 1, so EEPROM will not be selected. So with the help of A15, easily we can uh, we can extend our memory subsystem from 15 address lines to 16 address lines, and you can say 2 to the power 15 to 2 to the power you can say the 16 address lines we can address spaces we can have. Now another example, that 32K by 8 with the help of 8K by 8. So again we can divide. So address lines are not same, but data lines are the same. Address lines for the required system 15, and we have the 2 to the power 3. That means 13 address lines we have in our RAM chip. Okay. Now this you can design with the help of 4 RAM chip or 4 ROM chip, or here I assume I consider here the 2 ROM and 2 RAM chip. Okay, so again same way we can find out the address range. Chip 0 to chip 3 we can consider, and you have seen that 13 address lines we have in your given memory. So for that reason, A0 to A12 you have all zeros to all one for all the chips, but the A13 and A14 you want to use for selecting the ICs. Okay, so for 00 first chip, 01 for the second chip, 10 for the third, and 11 for the fourth chip. So obviously here you can find out the address range. Here A15 is missing, you can consider A15, assume the 0. If the A15 is not present here, so A15 you can consider the 0. So A15, A14, A13, A12. These 4 are the higher 4 bits. So the first digit of your address you can have from that 4 bits. So for the first chip 0000 to 0001. So for that reason 000H to 1FFH. For chip number 1, what has happened? 0010 to 0011. So that's why 200H to 3FFH. Chip number 2, 0100 to 0101. So 5. Isn't it? So for that reason 4000H to 5FFH. And chip number 3, that is 0110, that means 600H, and end address will be 0111, so that will be the 7. So for that reason it will be 7FFH. I hope you understand how to find the address range. And suppose that I have given only the design of two memory chip. You connect with the 2 memory chip. On that moment, you can use the any starting address, but remember that ROM always use the starting address 0. Because of that ROM, whenever you switch on your system, your program counter value always initialized by the value of 0. So and normally BIOS is stored into the ROM. So for that reason we use the 0000 address for the ROM, not for the RAM. Okay. Now these are the ranges and these are the circuit, and 2 to 4 decoder is sufficient for these cases. For this case, that is in a 0, 14 and 13 you can use for the chip select line, and obviously all the ROM and RAM chip has the 13 address lines. So for that, A0, A12 directly connect to the address lines A0 to A12. A13, A14 are not exist in the RAM. So for that two lines we use for selecting the chips. So these two you can use as a input of the decoder circuit. So 2 to the power 2 equals to 4 active low output lines you can have, and one line. Please better mute your. Please mute your. Okay. Now you see that here we don't have any other line. So on that moment, directly logic 0, I have used to enable that line. Okay. To enable the decoder, sometimes we can use the address lines. Sometimes we can use the fixed value. Here enable line is that E bar is an active low enable line. So I have used here the logic 0 value. Okay. Now, I hope this you understand. It is a very easy. I don't want to discuss. First, tell me that you do have any question, better after this. Okay, this is
Hello,
a
ma'am.
hello. See that
Yes,
here
ma'am, you're audible,
another
ma'am.
type of the IC. Huh? Here is nothing is different here. Just I have used the 4-bit data bus. So for the 4-bit, we have to design in such a way. We have the two type of the design. One is the horizontally expanded. Another is called the vertically expanded. Horizontally expanded means that, see here, 1K by 4. With the help of this, we want to design 1K by 8. So 8 means that 8 data bus we require. So for that reason, we need the two RAM chip. The 4 plus 4, that will be the 8 data bus we can get. So from one chip we can have the 4-bit, from another chip we can have the another 4-bit. Okay, a 4 lower bit and 4 higher bit. So address are both the ICs has the same address range 0000002 3FFH, and from the first we can have the D0 to D3, and second from the second we can have the D4 to D7. It depends on you. You can reverse. You can do that. So based on that is depends on your choice. You can select the chip for your for selecting the data bits. Now see the circuit here. In only one thing you try to remember: chip select right CS bar always it is 0 for the first the RAM, at the same time for the second RAM. Simultaneously both will be activated. Okay, so the CS bar, with the help of CS bar, both the IC will be activated, and from the first, or say from the first and also from the second, we have the 4-bit. Ultimately we have the 8-bit data bus. Okay, so and it is horizontally expanded. Suppose if we need the 16-bit, so in that we can consider the horizontally we can place the 1K by 4, and we can have the 16 data bits. Okay, so for the extension of the data bits, we can use the horizontally extension. Okay, now for the suppose with the help of this 4K by 4 we want to design. So on that moment, what will be happen? Vertically expanded, nothing else. And I hope you can find out the address range. Okay. Now these I don't know you have tried or not. You have tried better.
Ma'am, I could not get I could not get the 1K by 8 EEPROM chip, ma'am. In that case, will it be any different from the earlier problem, from the other problems, ma'am?
What better? I can't understand your question.
Ma'am, in question number 2, it's 32 KB using 1K by 8 EEPROM chip. So in that case, will it be any different from the other questions? That's what I was asking, ma'am.
No,
Like
no.
the
That is a suppose if I use only the 32K on that moment, this is the address space only I have mentioned. But
So then
here I
that case I
have
need
considered the
32. So ma'am, in that
KB.
case I need 32. I will need 32 EEPROM chips in order to fulfill it.
And here I have given 32 KB, B for bytes, capital B, that represent the bytes. So you can use the 32K by 8, no problem. I have not mentioned here the data bits, so you can assume the data bits are 8. Okay.
Ma'am, in that case, it has to be 32K into 8 by 1K into 8 if we need to get the number of chips. So in that
Yes.
case, would it be 32 chips? 32 EEPROM
Yes.
chips.
Yes.
Okay, ma'am. Okay, ma'am.
Okay. But it will be a big circuit.
Yes,
I'll
ma'am.
change the problem. It will take huge time.
Yes, ma'am.
Okay.
That's why I got confused. I thought I
Yeah,
was
yeah.
going somewhere
Okay,
wrong.
I'll change the problem. You can you can use two or three chips you can use, and you can find out the address ranges based on your design. Okay. And little bit I'll today I will explain little bit bank switching and address extension technique. This should not be in your syllabus, in your current exam. Okay. Now,
Okay, ma'am.
bank switching, it is a you can understand that it is a IC, or sometimes it may be happen a set of memory we can use as a bank. Okay, so I don't want to give some exact physical environment, but theoretically or hypothetically, I am trying to explain, because if I'm going to to explain detail description of a physical thing, then it will take huge time. So for that reason, I skip that part. But theoretically, how it will be implemented, that I want to explain. So this type of bank switching, what has happened, it is under software control, and with the help of some control signals of the processor, combine these two, we can do this operation, that we can place one decoder, and from the decoder one of the memory bank can be selected, and this environment you can have for your multi-user environment. You know little bit of the multi-user operating system. That means the multiple user can access the same processor or same computer system. Okay, and processor has the capability to execute the multiple program which comes from the different multiple user. Okay, and most probably next semester you will study the operating system. There you can understand the multi-user multitasking operating system. Processor has the very high speed compared to the what human can do that. So human cannot understand that processor is doing in different way. Okay, they are sharing the different real time of the CPU they can manage. So user cannot understand that processor are doing in that way, and for that we can use this type of the environment, and bank can be switching, and that can be done with the help of software, as well as that means programming at the same time with the help of some control signal. You should remember that that is a with the same as your decoder, it will act. It gives some inputs to the decoder, and one of the input can select to one of the memory bank. Okay. And another is the address extension technique. What is happens, processor has some address bus, processor has some data bus. Address bus content normally comes from the program counter or instruction pointer. So you know the name program counter, that already I have explained, 8085 architecture. But some processor we use the term instruction pointer instead of the program counter, but function of the instruction pointer and program counter is the same. So whatever the content of the program counter, basically that transfers to the address bus, and that will be act as a offset. And whatever the registers, internal registers processor has, normally that are used for storing the data, or you can say the operands. But sometimes that register can be used as a address, or for storing the address. So that address can transfer to the data bus, and processor can use that address as a base address. Ultimately, offset and base address can be combined, and we can have the physical address of the memory. So this is here I have given this figure from the book of your Rafiko German, but you try to remember many other signals we removed that. Just we want to simplify the figure. Okay, so data, when data bus is used as an address bus, on that moment with the help of latch we can use that as a base address. On that moment you latch will take some other control signal. Based on that it can generate the base address. Okay, so you understand that latch means that this is a sequential circuit, so one of the input should be the clock. Okay, that that we have removed from the that this design. Because of that we want to simplify the diagram, nothing else, but we try to understand that it is possible that we can generate address, we can get the address from the address bus as a offset, and we can have the address base address from the data bus, and we can combine that base address with the offset to generate ultimate physical memory address. Clear? Another example of this, another way we can do this type of the extension, all are the memory address extension technique. See that here 74610, it is a basically one IC, and this 74610 IC, what is happened, it has one decoder circuit, and it takes the 4 input, that decoder circuit, and obviously output lines will be 2 to the power 4 equals to 16, and these 16 lines can select some base register. Some I should not say that 16 lines can select the 16 base registers. Okay, where each base register has the 12 bit. Okay, that can generate the 12 bit number. So now processor can send the 16 bit address, and out of that 0 to 11, that means lower 12 bit we can use as an offset, and with the help of 74610 IC, upper 4 bit we can extend to a 12 bit base address. So ultimately we have the 0 to 23, that means 24 physical memory address. So lower 12 bit as it is, it will be offset. Upper 4 bit of the original address that we can convert into the 12 bit base address. So in this way we can also expand. Okay, so some processor beta.
Now, could you explain this again? I didn't get this part, ma'am.
Yeah, see that processor generates the 16 bit. Now lower 12 bit, that means 0 to 1 we can use as an offset. Okay, and upper 4 bit means 12, 13, 14, 15. If that will go to the input of decoder, then decoder can generate 2 to the power 16 lines, and one line can one output means one output of decoder line can select one of the base register. Suppose here the 16 registers we can connect with the help of the 16 decoder output lines. Clear? Where each register can has the 12 bit, so register can also generate the 12 bit address, and that address we can assume that this is a base address. So now offset and base, how many bits we can have? 0 to 23. Offset has the 12 bit, and base register, from the base register we have the 12 bit base address. So 12 bit, so 12 plus 12, total we have the 24 bit address bus. Now it is clear better? And it is possible if you change the number of bits you register, you can change that, maybe the 10 bits. On that way it will be 0 to 11, that means 12 plus 10, on that moment it will be 22 instead of 24 bit. That depends on your design. Clear better?
Yes,
now it is clear?
Yes, yes, ma'am.
Yeah, that already you have done your digital electronics also. Decoder from, you can extend that with the help of the register. Now, this part I don't want to explain. That is, please you study from the Rafiquzzaman. That is magnetic tape, magnetic disc. These two things you try to study. This is not very tough. Please you study from that book. Okay. And this assignment not necessary not necessary you do now. Later you will do, after exam you will do that. Okay. And a little bit I want to say about your that is 8085 better. Can you see the screen better?
Yes,
8085.
ma'am.
First slide you can for the exam purpose. First slide you can skip, and second lecture you please you study. Okay, this what I have considered. Just check that. I try to understand the pin. Try to understand the what are the buses here. No need to remember others. That is for interrupt signals and many other control signals are there. No need to remember. Only address bus, data bus, and control signals are available. This you try to remember. Okay. No need to remember this internal diagram. Only you understand that what are the registers are available and what are the other, that means arithmetic logic units are available. Clear better. So and here this part is very important, that what are the flags are here and what are the purposes. You know that sign bit, D7 bit is represent the sign bit after operation. Whatever the D7 bit, that will be stored into the sign bit, that is the D7. And if the result is 0, on that way Z flag will be 1. And if generate any carry, on that way carry will be 1, otherwise 0. Parity bit is that parity even and parity odd. Parity even means that number of after the operation the result if you have, then compute the number of ones. If number of 1 is even, on that moment parity bit will be 1, otherwise it will be 0. So you try to remember the purpose of all the you can say that all the flags. Okay, you have the different type of instruction. Only you study the data transfer, arithmetic and logical. No need to remember branching and control signal, control instruction. Okay, you study the data transfer, arithmetic and logical. Little bit you try to study data transfer, move, MBI, LD, ST, LHLD, SHLD you have done. This part you can skip, and please you study this arithmetic instructions. Okay, and these logical instructions please you remember, and no need to remember rotate instruction. Only just other that compare and the complement of accumulator, complement of the carry flag, set carry flag. You try to remember all these things. This is not required for this exam. Okay, later you will do, but in your final exam I will give the question from here. But for this mid semester exam, no need to remember this instruction. Stack information is not required. But if please you study the programming part, maybe I can give some question from the programming part. Okay, only 1 2 3 very nicely you try to do. Okay, better. And this you can that branch instructions are available, so you can skip this two part. Addressing modes very nicely you have to study. Clear? So you have many slides in your this part of my lecture. Please you study the at least lecture 2 very carefully. You don't have enough time to come. Question is very easy, but uh, but you should practice. You should know the theory. Otherwise, you cannot compute the result. Okay, beta. So this part you can complete. Any other question regarding your exam?
No, ma'am.
Do you have any question, beta?
No, ma'am.
So prepare for your exam. Okay, next class I will start your execution unit. Friday, Mustafa, you have class. On that class, I
And
will.
ma'am, when will we get the slides for bank switching tech?
That today I can give, no problem.
Okay, thank you, ma'am. Thank you.
Okay. So now I can leave. So best of luck for your exam. Okay.
Okay. Thank you.
Okay, beta.
Thank you, ma'am. Thank you,
Okay.
ma'am.